This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the second derivative test. Our first notion is the notion of concavity. If the second derivative at c is positive, then f is concave up. What does that mean? It means its shape is bending this way. It looks like the graph of y equals x squared, so bending upwards. If the second derivative is negative, then f is concave down, in which case it looks like the graph of y equals negative x squared. And the concavity will tell us something about whether a critical value is a minimum or a maximum. We're going to look at the second derivative test. Our first step is to find those critical values. Now, with the first derivative test, the critical values were where the first derivative was 0 or where the first derivative doesn't exist. We can't really handle problems where the first derivative doesn't exist with the second derivative test. So we'll just focus on cases where the first derivative is 0. Next, we look at the second derivative evaluated at that critical point. So if we have a critical point, so it has a horizontal tangent, and we know the function is concave down, we're going to have a local max. And I hope you can see that if we have a concave down situation, the point with the horizontal tangent will indeed be the highest value in the neighborhood. That will be a local or a relative maximum. If the second derivative is positive, then the function is concave up. So if it's concave up, it's a right side up parabola, in which case the function f would achieve a local min there. Can we see that? Positive concavity, horizontal tangent line, that will achieve a local min or a relative min at that point. Now, if the second derivative is 0, the second derivative test fails, so you can't use it. So you've got to go back and use the first derivative test to find any local mins or maxes. Here's our first example. F of x is negative 3x squared plus 12x minus 5. We want to find critical values. We want to find points where the first derivative is 0. So using that second derivative test, first derivative, f prime of x, set it equal to 0. 6x is 12, x is 2. That is a critical value. Now we could use the first derivative test. We could try on either side of 2 to see if the function is increasing, decreasing, or decreasing, increasing. But instead I'm going to use the second derivative, which is going to get our answer fairly quickly here. So 2 is our critical value. What about our second derivative? F prime of x is negative 6x plus 12. So f double prime is negative 6. Second derivative is constant, is always negative. If it's negative, that means it's concave down. So if it's concave down, what does that look like? We have an upside down parabola for a concave down situation. If that's the case, then the function f will achieve a local maximum at x equals 2. We can look at the actual function. Looks like this. F of x is negative 3x squared plus 12x minus 5. Indeed, you can see that that function achieves a local maximum at x equals 2. You can also see that it's concave down everywhere, in which case we're going to have a local maximum. Our next example is f of x is 2x cubed minus 3x squared minus 72x plus 11. We're going to use the second derivative test again, but our initial strategy is to find the critical values. Take the first derivative, set it equal to 0, and solve for x. First derivative, 6x squared minus 6x minus 72. Set that equal to 0. You'll notice each of these terms has a multiple of 6. So we can divide that 6 out. 6x squared divided by 6, 1x squared. 6x divided by 6 minus x. 72 divided by 6, 12 with the minus sign there. Then factoring this will be x minus 4 times x plus 3. So if that's the case, x minus 4 is 0 or x plus 3 is 0 because 6 can never be 0. So our critical values will be x is 4 or x is negative 3. Now to determine if those are mins or maxes, we're going to go ahead and use the second derivative test. So we have our critical values. We're going to plug those into f double prime of x. So what is f double prime of 4? Is that going to be concave up or concave down? That'll tell us if it's a min or a max. What's f double prime of negative 3? Concave up or concave down? That will tell us if that is a minimum or a maximum. There's our first derivative. Our second derivative then is 12x minus 6. I needed f double prime of 4, one of my critical values. 12 times 4, 48 minus 6 is 42. That's positive. That's concave up. We have a positive concave up situation. We know that the function will have a minimum, a local minimum at that value. So we'll say f achieves a local min at x equals 4. The other critical value was negative 3. So f double prime of negative 3, 12 times negative 3 minus 6, negative 36 minus 6, negative 42. Concave down. If the concavity is negative, it's an upside down parabola, at which case we will achieve a local maximum. Where? At x equals negative 3. Now what does the real function look like? Will we see the min at 4? Will we see the max at negative 3? Min at 4, sure enough. Now notice the y values get very, very large, positive and negative, taking a look at the scale here. But indeed, local min at 4 and a local max at 1, 2 at negative 3. Horizontal tangent there, horizontal tangent here. Notice it's concave down at negative 3. Notice it's concave up at positive 4. Our next example is going to be g of x is x squared plus 1 over x. We're going to use the second derivative test to find mins and maxes. First, we've got to take the first derivative to find the critical values. So g of x we're going to rewrite as x squared over x plus 1 over x. That will make it easier to take the derivative. Now you could have used the quotient rule here to do the evaluation, but this will be a little simpler. Reducing that x squared over x is x. 1 over x is x to the negative 1 power. We want to get the first derivative. The derivative of x is 1. The derivative of x to the negative 1 is negative 1 x to the negative 2. How do we write that? Let's rewrite that as 1 minus 1 over x squared. That's our first derivative. You will notice it does not exist when x equals 0. You will notice the function does not exist when x equals 0. So if we were doing the first derivative test, we would have to pay attention to that. That is a point where the derivative does not exist. Now it's not going to be a min or a max because it's not in the domain, but we have to at least think of that on our number line. But we want to do the second derivative test. Let's find our critical values where the first derivative equals 0. So when is 0, 1 minus 1 over x squared, of course, when 1 over x squared equals 1. Multiplying by both sides by x squared, because of course it can't be 0, we get x squared is 1, subtracting 1, x squared minus 1 is 0. That factors into x minus 1 times x plus 1 equaling 0. So x minus 1 is 0 or x plus 1 is 0, so we get our critical values where the first derivative equals 0 at x equals 1 or x equals negative 1. Now to determine if these are mins or maxes, we have to take the second derivative, if that's going to be our model, and plug those critical values of 1 and negative 1 into the second derivative and determine concavity to identify the result as a minimum or maximum. So here's our function g, here's our function g of x, 1 minus 1 over x squared. Our critical values are 1 and negative 1. I want to get the second derivative, so this version will be easier to work with. The derivative of 1 is 0 minus the derivative of x to the negative 2, negative 2x to the negative 3. So you'll notice I have here second derivative, derivative of 1 minus derivative of x to the negative 2. Derivative of 1 is 0. The derivative of x to the negative 2 is negative 2x to the negative 3. Watch these. Minus negative, so that just becomes 2 times x to the negative third, or 2 over x cubed. This will give us our concavity. I'll plug in the critical values of 1 and negative 1 to determine if 1 is a min or a max, to determine if negative 1 is a min or a max. So first let's take a look at 1. G double prime of 1 is 2 over 1 cubed, that's positive 2. That's concave up. If we have a concave up situation, the function will achieve a relative min, a local min at x equals 1. Regarding negative 1, so that's our other critical value, we're going to plug negative 1 into the second derivative to determine the concavity. So g double prime of negative 1 is 2 over negative 1 cubed. Negative 1 times negative 1 times negative 1 is negative 1. 2 divided by negative 1 is negative 2. So it has negative concavity, concave down. Critical value is negative 1. It has a horizontal tangent there. It is concave down. Therefore, the function must achieve a local maximum at x equals negative 1. Let's take a look at the actual function. You can see what we have here. So what's happening at negative 1? Horizontal tangent, local max, highest in the neighborhood. Certainly not the highest everywhere. All of these numbers are higher. But negative 1 is the highest in any neighborhood around negative 1. In a reasonable neighborhood around negative 1, and positive 1 is a min, local min. In his neighborhood, the y value at 1 is lower than anybody else. So indeed, we can see that G achieves a local min at x equals 1. There that is, and a local max at x equals -1. Take a look at one more function. If f of x is x to the fourth, we want to try to use the second derivative test. We take the first derivative, set it equal to 0 to find the critical values, and the only critical value I get is 0. And the derivative always exists, so there are no other critical values for me to work with. But the second derivative is 12x squared. If I plug 0 into that, I get a result of 0. If the second derivative is 0, the second derivative test fails. So you cannot determine whether their critical value is a minimum or a maximum using the second derivative test. But you can with the first derivative test. So just a quick reminder. 0 is our critical value. Our first derivative is 4x cubed. We're going to choose numbers on either side to see if it's increasing or decreasing. To the left of 0, I chose -1. To the right of 0, I chose +1. So f prime of -1, plugging -1 in for x, 4 times -1 cubed. -1 cubed is -1 times -1 times -1. It's -1. We get f prime of -1 is -4, so it's decreasing on this interval. On the interval from -infinity to 0, the function is decreasing. And then plugging in 1 into the first derivative, f prime of 1 is 4 times 1 cubed, which is +4, so it's increasing there. Well, from the first derivative test, if it's decreasing to the left and increasing to the right, we know we have a min. So f will indeed achieve a local min at x equals 0. By the first derivative test, the second derivative test was inconclusive. And just a quick look at that graph, you'll see that that's the case. Decreasing to the left, increasing to the right, horizontal tangent there. But you'll also notice it's pretty darn flat, so we have no concavity to speak of at 0. So that's why the second derivative test failed. And that will conclude this lesson.